Good morning, everyone. Today I'm gonna talk about two parts, apparent weight and then gravitational force. In apparent weight is kind of, as you can see here, apparent weight is your sensation of weight changes. For example, on a roller coaster or sometimes in an elevator. So the force you feel, but basically your sensation, in other words, the force you feel is actually the contact force that supports you. So basically, whenever you are asked to find apparent weight, is simply asking you to find the normal force. Okay. Again, let's go over what we did last time. We talk about, circular motion, and again, in order to have a circular motion, you need the net force toward the center of the circle, right? So let's see the roller coaster case here. The bottom case, we already, solved the same similar examples last time. At the bottom here, there are actually two forces acting on the roller coaster, right? The first one is a weight acting up, and then normal force acting up, and the weight is acting downwards. So then this time normal force, which is whose direction is outward, must be greater than the weight in order to have the net force toward the center, which is outward of the circle. However, at the top, because both normal force and weight is acting downwards, so then you have a anyway net force toward the center, which is downward. But you see, you can compare these two normal force. First, upper normal force, and then down, normal force. The down one is much greater than the normal upper one. That's why you feel, imagine you're on the roller coaster, and then you're at the bottom position. Then how do you feel? You feel heavier, right? But when you are at the top of the roller coaster, you feel lighter, right? So that's why you feel different sensation of a normal force basically, right? So again at the bottom you see your normal force is much greater at the top, right? So this is the picture, right? So the figure shows the free body diagram, which we show, right? So then you see normal force here down is always a greater than the top. Okay? You can also say, you can also interpret this one in terms of the, circular motion. For example, at the bottom part, your normal force and then weight, which is a n minus w. Again, Newton's second law for the central of feather acceleration. Again, this is a ma, but where a is a b square over r, right? So then the passenger's apparent weight, in other words, n, is you have to move w to the other side. So what you're gonna feel, in other words, apparent weight, in other words, normal force is gonna be your w, your original weight, plus a mv square over r. So that's why it's greater than your true weight. Right? However, at the top, your normal force plus weight is a mv squared over r. But this time, then your normal force, which is apparent weight, is your mv squared over r minus omega, right? So this time, your normal force, as you see in the pictures previously, diagram, your normal force is smaller than your usual weight, right? So that's why you feel light. Right? So as the car goes slower from, comes a point where n becomes 0, for example. So then the speed for n0 is called critical speed, which is called VC. So that because n to be 0, we must have a mv square, bc square actually, r must be same as your weight, right? Then your normal force will be 0, right? So in other words, your net force is always W plus minus N, right? So especially when you have a 0, critical speed, that means that this part is a 0. Then this W itself is what? mv square over r. So your VC, I'm sorry, this is a VC. VC is simply m rw divided by this m down denominator, right? And then square root of it, right? So then you see VC will be root to GR, and then you will see later we'll use this formula a few times, okay? And then in other words, the critical speed is so this the critical speed is the slowest speed at which the car can complete the cycle. So now a physical textbook swings back and forth as a pendulum, and which is the correct free body diagram. So then now you see what is the force acting on this book. Of course, tension acting upward. Of course, weight acting downward. And these two is the only force, okay, acting on this book. Don't assume there's one additional force acting horizontally. You probably choose D or E because the book at this moment is moving to the right in order to have a circular motion, right? But again, you don't have a circular motion because of this side force. You have a circular motion because what? Net force is toward the center of the circle. So again, in order to have a the circular motion, you need a net force toward the center of the circle, which means T must be greater than the W. So the answer is C. The same question, there's two forces acting on the car. Of course, the normal force acting up and the weight acting downwards. Again, there's no force acting horizontally to maintain this circular motion. But this case, again, your net force must be toward the center of the circle where your center is below here. So your downward force, which is a W, must be greater than the upward force, normal force. So this case, your answer will be A. Same question as we already see, right? Roller coaster at the top, two forces acting on it, right? Weight acting downwards, normal force is perpendicular to this surface is a down. So then the answer is E. And then, because both forces are acting downward, which is toward the center of the circle, right? So this makes sense. And then a coin sits on a turntable as a table, steadily rotate counterclockwise. And then what force or forces acting on the plane of the turntable? Same, right? So you have a net force toward the center of the circle. So you don't need these side force. You only need net force toward the circle in order to have a circular motion. So the answer is A. And the same, if this is what is the, you know, correct diagram, but basically the same diagram, but now it's a three-dimensional. You can also have other two forces. One is up, the other one is a down, right? So then the answer is C, right? Upward force, this is a normal force. Downward force, this is a weight, and this is a horizontal force. This is a static friction force. Sorry, this is a static friction force, right? And this is a cars turns corner on a banked road as we did before, right? So which of the following diagram, free body diagram of the, cars? Again, you have a weight down, so you need weight, weight. This doesn't make sense. This doesn't make sense. And then you have a normal force perpendicular to the surface. Okay, okay. And then what is the force is acting? You have a static friction force, right? To the horizontal, to the left, right? So then your answer is E, right? You have a static friction. So the differences between this banked road question and the previous one, is the previous one we assume there's no friction. So there we assume that we don't have this force. This time they assume they don't say friction force is non-zero, so you must assume friction is non-zero as well. And then next one is the circular orbit and the weightlessness. Now let's assume you have a very strong shoulder. I'm not sure I'm not sure how many of you actually play baseball but let's assume you have a really strong shoulder and then you throw the ball, right? This is your earth, right? Our earth, so that should be in a few thousands of miles, right? And then if you are more stronger, if you're stronger, then you probably throw more, and then stronger, throw more. But at some point, if you throw the ball extremely strong, what's going to happen is that the ball will hit your back, right? So this is the principle of a satellite. And the thing is, this satellite or this ball has a what? A circular motion, right? So this is exactly the same pictures we had so far, right? Again, we have a circular motion, and then in order to have a circular motion, what do we need? We need net force toward the center of the circle, which is the center of this planet, right? So what will be the that force acting on this ball? That's the weight of the ball will be the source for the centrifugal acceleration for this circular motion. Right? So if the launch speed of the projectile is sufficiently large, so if you can throw the ball extremely, strong, there comes a point at which the curve of the trajectory and the curve of Earth are parallel. In other words, the ball and the comeback hit your back, right? Such a closed trajectory is called orbit, right? Which is a path of a satellite, right? So then this is nothing but your force, your acceleration, the force times mass. So your force for this case, as I said, is mg, right? So then mass is m. So then you see the acceleration is a g, of course, right? Because it's a free form motion. Your acceleration must be g, right? And again, your acceleration is a g. So that means your v squared over r will be g as well, right? Because why? Newton's second law, F equal ma. So if you multiply m everywhere, this makes sense, right? So this is nothing but canceling m. Then you see v orbit will be root 2 gr. So that means, okay, you know what is a g10. You know what is r, radius of the earth, which is a big number. So then you see that v orbit is not a small speed. Right? So this is a kind of the minimum speed of your satellite. So which is about 8,000 meter per second. And then we can also calculate the period of the satellite. Why? Because again, same as the last lecture, right? If you know the velocity, your time, which is the period that will be given, right? So in other words, your v is a 2 pi r over t. So you can find the time as well, which is a 2 pi root 2 r over g, where r is the radius of the earth and then g is simply 9.8. Then you see it's about approximately 11 hours. Right? So the next question is a very important, you know, section about Newton's gravitational force. So the gravitational force is a very simple. This is a force between two objects due to their masses. So the gravity is a universal force that affects all objects in the universe. So Newton proposed that the force of gravity has the following properties. The force is inversely proportional to the square of the distance between two objects. So now let's assume we have a first object m1 and the second object are m2, and the distance between these two objects is r. So then now the force is inversely proportional to r squared. And then the force is directly proportional to the product of the two masses. So this is a m1, m2, and then we have a coefficient g, which is called gravitational constant. Okay? So the gravitational force between two objects due to their masses, this is a new equation. It's a very simple. G times q m1 m2 divided by distance. So where G is you see G is 6 times 10 to minus 11. You see G is a very small number. So this G is a very small number. So that's why. So this gravitational force you can apply, this one, any case. Assuming, you're in Georgia and New Jersey, right? So we are, I'm here, you're here, right? Sorry, I'm not here. I'm not there, right? So I'm here, right? East Coast here, and then you are here. And then the distance is, I believe is a few hundred, a thousand miles. I don't know, but roughly it's far, far away. So that means this r is another small number, and then square, of course, it makes r square even smaller number times another small number m2 m1 times your mass my mass is a very tiny compared with the g and over r square. So every numbers are very small, so that's why we cannot feel the force by each other, right? So again, the one I want to say here is this gravitational force is everywhere. So in other words, you are attracting me toward you. I'm attracting you toward me. And at the same time, you are attracting, your pencil right next to you and your, laptop, in front of you. You're attracting every single object around you. Okay, but we cannot feel that force because G is very small. And the mass U and the other object is very tiny. There's no way we can feel the actual force. But that doesn't mean the force is a zero. For example, gravitational force between two giant lead spheres is a zero point zero 0.01 Newton when the centers of the spheres are 20 meter apart. So you have a really, really big lead, and then this is a distance is a 20-meter apart. What is the distance between their centers when the gravitational force between them is 16 times greater? So force is gonna be now 16 times greater. So what is the initial force? Your initial force is G times m1 m2 divided by r was 20 squared. But now you want to increase this force 16 times more. Why? You have the same G because we don't change mass will be the same, right? So in order to have a greater force, what happened to the distance? You must have a closer distance, right? But how many times? The distance, if your distance is 2 times closer, your force will be increased by factor of 4, right? Because why? The force is proportional to 1 over r squared. So the answer is your distance must be 4 times smaller. So the answer is 5 meter. Okay, and another question is you are seated in your physics class next to another student 0.6 meter away, right? So let's say you have your friend and 0.6 meter away, and then estimate the magnitude of the gravitational force between you. You can also use your real mass, but or you can use a 65 kilogram. Again, the force is a G, 6.67 times 10 to minus 11 times 65 kilogram, and then another 65 kilogram. You can change this number, and then you can also change this distance as well, depends on the real distance. But whichever number you actually use, you see this force is extremely tiny, right? So order of 10 to minus 7 Newton. This is a extremely small force. That's why you cannot feel the force. So the next question here, okay, the force of a planet Y on planet X is the magnitude of a x fx on y. So then question is here, we are comparing two forces. Force, acting on planet Y by planet X versus force acting on planet X by planet Y. But this is exactly what? Newton's third law, right? So the force exchange there, they must be the same force. Right? They both have the force what? G times 2m times m divided by r squared. They both have the same force. And the gravitational force between two asteroids is about 1, 2, 3, 4, 100,000 Newton. And then what would be the force if the distance between them is doubled? If the distance is doubled, then your force must be smaller. But how much times smaller? Because again, your force is proportional to 1 over r square. If you increase the distance 2 times, the force is gonna be 4 times smaller. So the answer is A. Right? And then now the definition of weight. If you travel, so now let me write very important thing here. So so far we talk about gravitational force, which is defined as a g m1 m2 over r squared. So this is a force between two objects. So now question is, what if the first object is simply Earth and the second object is yourself? Then what is the force must be given? Then this force will be changed. G, instead of m1, I will call me, which is the mass of the Earth. And then times, again, m is your mass. And then distance between you and Earth. So now this picture is like Earth and you, right? So the distance between you and the Earth is gonna be radius of the Earth. This is a radius of the Earth square, right? So this is actually the force acting on you because of the Earth's mass. In other words, this is called weight, which is a mg. So then now you see the definition of g. Definition of g is this combination. This combination will give you 9.8 meter per second square. So in other words, because of g, we already know it's 6.67 times 10 to minus 11, right? If we know mass of the Earth, and then if we know the radius of the Earth, then if you just simply calculate this three number combination, you will see gravity of the Earth is gonna be 9.8. But you can also do the same logic, apply the same logic to the, for example, to moon. So the only, if we are looking for, gravity of the moon, it's very simple. You simply replace this part, mass of the moon, and the radius of the moon. Then this combination will give you gravity of the moon. So basically, if you know a planet's mass and the radius of it, you can always find the gravity of each planet. And then gravity on others. So basically, again, if you're here, gravity will be mg. For example, this is moon. Now again, this is a g times a m moon divided by r e moon, r m moon, right? R moon square, right? And then big G perspective, this is a G here, this is a G here, right? So if we use values for the mass and the radius of the moon, we see 1.67, which is about 7 times smaller than the gravity of the moon. So then now, so if you have a we have a 70 kilogram person, right? And then with a 80 kilogram in a space suit, and then his weight is now have a 150 mass, but times what? Instead of a 9.8, 3.62. That's gonna be your weight at the moon. So the planet acts as a free fall acceleration 8, right? Which is a slightly less than the Earth at the surface. Planet Y has a twice the mass and then twice the radius of planet X. Then what will be the planet Y? Planet Y is G, right? So then now you see planet Y, planet X, gravity is again G times mx divided by r x squared. That is a gx, right? And then now we are looking for gy, which has a mass is a twice the mass. So instead of mx, you have a 2mx, right? And then distance is 2 times. So now 2rx now is a square. So then now if you see the number only, g mx over rx squared still have it. But now you have a 2 in front and then 4 denominator. So the answer is a half of it. So the answer is a B. Right? Similar question, right? Has a what is the when the greatest to G value, right? Again, the first one is what? The combination G times a M over R square. This is a GA, right? What is your GB? Same thing as a GA, but now you have a G, but now instead of a M, you have a 2M. Instead of 2R, you have a 2R square. So then this is a 2 in front, 4 in front. So 1/2 times the GM over R square, which is a GA. So this is half of it. And then how about number 3? GC will be G times the mass is a 3 mass and then divided by 3r cubed. So now this is a 1/3 times a g a, right? So the answer is a. And then Mars has 2 moons, each much smaller than the Earth's moon. Basically, the smaller of these two bodies, Daminos, is quite spherical, but we can assume this is a sphere whose radius is 6.3 kilometer, and the mass is given. What speed would the projectile move in a very low orbit around them? So this question is basically throwing the baseball, right? That's what we talked about, right? So before we talked about, we have to find the g of this planet first, right? So the small g of this moon is gonna be what? G times mass is a 1.8 times a 10 to 15 divided by r. You have to convert r to meter square, right? So then if you calculate it, you will see G will be 0.003. So you see this number is extremely small. So the gravitational force you will feel it's not going to be really strong in this planet, okay? But now then you can find the orbit speed, which is a root 2 gr as I showed earlier, right? So then the speed is simply, you see, very small. It's just a 4.3 meter per second. So then now, if you can, with a good jump, for example, you can jump horizontally, then you could easily launch yourself into an orbit around the Deimos, right? So that means yourself, can be a satellite of the moon. Okay, this is it. And then this is end of chapter 6. So I will assign another homework, but that should be due after our next exam. Okay, so I believe that that is due, next Thursday or Friday. Okay, thank you. If you let me know about this lecture or about the exam, please let me know. Okay, send me an email. Thank you. Have a great day.